Okay, we're going to start our introduction to XFLR5, and we're doing this through an analysis of the Piper Cherokee. So go back and look at design problem 6 with the Piper Cherokee planform. This is what we want to be able to model. Now for the current problem, we're only going to be looking at the wing, but eventually we'll be able to do the entire aircraft to lesser degrees when we include the items such as the fuselage, but certainly the empennage will be able to fully model along with the main wing. So we want to look at the geometry. You'll have to take down numbers for this because when you start to enter in the values for the wing planform, you'll need to know different station settings. So if you look along the semi-span of the wing, so you'll have to not only know what the entire semi-span length is in inches, but also the geometry such as the root chord right here, as well as locations of the flaps, not only along the chord but also along the semi-span to do a fully accurate geometry of that Cherokee planform. Now to simplify this, this is essentially what we want to be able to model is this planform right here. Relatively straightforward. Notice that we have a little bit of crank here within the wing, but other than that it is a straight Hershey bar wing type of profile. So it'll be relatively straightforward to model, but we still have this crank that we have to include with a larger root chord and smaller tip chord. We can take another look at this by looking at another sectional view of the plant three view of the Cherokee with the top as well as the side. So note from the front view you can see that there is a significant dihedral. We'll also be able to model that as well. Okay, so let's go ahead and get XFLR5 started up. Now what you'll notice when you run this program is you'll have a couple different options that you can utilize for this. It's really two programs in one. It's both a panel solver, just like XFoil, and it's actually built on top of the XFoil engine or the source code, as well as a vortex lattice code, which allows us to do both the 2D using the panel solver through XFoil, as well as the 3D solution using the vortex lattice code. So these first three options that you have here, direct foil design, and XFoil inverse design, are options that you can also do in XFoil. For now, all we really want to do is this XFoil direct analysis. Excuse me. So when we come back and look at this, we're going to first generate an airfoil, and let's just go through this process pretty quickly, starting off with a NACA foil. So let's do a 0012 here with 100 panels. I'm going to name it to NACA 0012, and there is our airfoil. Now for this particular airfoil, what we want to be able to do is look at the entire lift curve slope and the drag polar, and so we'll come back and do that entire analysis. For this current foil, kind of hard to see here, so let's change this color and make it a little more obvious. Okay, so there's our NACA 0012. Now we have a lot of options up here, so we're just going to keep to the very simple basic analysis, so we're not going to go through all the bells and whistles. So what I want to do is define analysis, and notice you have lots of analysis types here as well. We're just going to stick with the type 1 for now. You can come back and explore this some if you want to later. And notice it goes through an automatic naming scheme where the name of this particular analysis is based upon the type, Reynolds number, Mach number, as well as your critical end number here. So this is the XFoil default, so you can leave this as is. And let's just go ahead and we'll run a value of Reynolds number of 500,000 for this particular analysis. Now once you're set, then you can come over here and control your alpha sequence just like you would in XFoil, and we'll go ahead and run a viscous analysis for this as well. Run through, there's our analysis, and now we have our drag polar, lift curve slope, moment, and then the transition locations and the lift to drag ratio as a function of alpha. Now, just like we can in XFoil, we can come through and modify the foil. So let's just come in for this particular analysis. What we need to do is be able to add in flaps. So we're going to add in a trailing edge flap of 5 degrees flap down. Apply that, and we're going to name this the NACA 0012 flap. We'll come back and utilize this later. Again, you can barely see it there, so we'll edit our color. We'll make this one orange there. Okay, and so there's our NACA 0012 with a little bit of a flap, and then we can come in and define another analysis for this, and then run this particular analysis. Okay, and we can go back and look at our two sets of drag polars that we have. Here is our baseline NACA 0012, and then here is our flapped NACA 0012. Lift curve slopes for each, moment coefficients, and lift to drag ratio. Note that even though our maximum lift coefficient is higher for the flapped NACA 0012, the overall lift to drag ratio is higher as well, and that's not always going to be the case. It really depends upon the details of your geometry. Notice that when we came back and did this particular analysis, we did this for a Reynolds number of 500,000, and so we can come back and change this, and that way we're comparing apples to apples instead of apples to oranges for this particular case, and then we can come back and run this analysis again and then do a comparison between those. Okay, so again, we can do this for airfoils we can load up as well. So we're going to load the NACA 6 series airfoil that we're using on the Piper Cherokee, and then define an analysis for that particular airfoil as well. So again, we're going to make sure we keep our Reynolds number the same between the two, and then we'll call this the N6 for our NACA 6 series airfoil, and then run the comparison with this one. So now here's our NACA 6 series, and notice it does a much better job in terms of lift to drag ratio than the NACA 0012 does, which is kind of what you would expect being a cambered airfoil with our NACA 6 series. Now we could also come in and add a flap to this one as well. I won't go through that particular process for this case on this airfoil, but you would need to do this for the actual homework. Okay, so now we have this data stored, and we can use these airfoil drag polars for a plan form analysis for the vortex lattice approach. Now, just as an aside, you can use XFLR5 in place of XFoil. Notice it does give you the same capabilities. XFoil is still more powerful in terms of all the details that you can run and analyze, particularly when you're looking at the various boundary layers. But this is pretty useful if you want to come in and be able to look at different parameters for your airfoils. Be able to do comparisons between them, and it's also got a GUI, so sometimes it's a little easier to use. Now what we're going to do next then is go to wing and plane design. So in this particular case, what we need to first do is start defining a geometry. So we're going to define a new plane. We'll call it Cherokee here. And note we have a lot of options in here. For now, we're not going to worry about things such as the plane inertia or the body or even the elevator and the fins. We're going to ignore these. Notice you don't have an option here of deselecting the main wing. We need to at least have that. So we're going to define what the main wing geometry is. So when you pull this up, you start off with a very basic wing. And so here's where you'll have to go back and look at the detailed geometry of the Piper Cherokee. So first off, for our root chord that we have, we need to start off with a chord of 84 inches. And you'll have to modify each one of the cells, since it starts off at values that are to be a little bit out of whack with what we want for a full-scale aircraft. Note for this particular case, you will have to come back and you'll look at the correct values that we have for the Piper Cherokee. So just keep in mind that what you'll start off with here and the numbers that I'm going to be using will not be the numbers that you'll want to put in for the final values of the span. Now what we'll have to do, you start off with two sections, is you'll have to include additional sections. So we'll insert a few wing sections after section 2 and then section 3 here. And so I'm going to make this with the correct crank by using the chord on the outboard sections of 63 inches, and then there's an offset of 21 inches to kind of give us that correct crank that we have in the inboard section of the Cherokee wing. Now just for the outboard sections, what I'm going to do is just add 2 more sections in here. So we'll just say 100 inches for this next section, and then 180. And that 180 will actually give us pretty close to the actual span that we'll see on that Piper Cherokee. So this is pretty close to what the final should be, minus some details, right? And I'll let you figure out what those details need to be in to fix that. Oh, sorry. I need to correct these two here with 63 inches and 63 inches, right? And so that's pretty close to this final kind of Hershey bar wing with that inboard section that connects to the fuselage. Now what you'll note is you have a couple of other variables that you can change on here. For example, you can set the dihedral angle, which is 7 degrees on the Piper Cherokee. Upside down here, and so it's going to look a little bit like this on that Piper Cherokee. And you'll note that you'll have to change this for each one of these sections as you go through. Otherwise you'll get a gull wing and you don't need to change anything on the final outboard section. So now you have kind of that correct dihedral that you have on the Piper Cherokee. Note you can also add twist in here, don't worry about that. The final piece you need to add is the actual airfoil. And so notice we selected a couple of different airfoils that we ran, including the NACA 0012 and then the NACA 6 series airfoil. For our Cherokee, we're going to go throughout with the entire 6 series airfoil. And then we're set. And that's all the geometry. Now you will have to make sure that you select a foil for each wing section. If you do not do that, then it will not correctly run. So you need to be able to do that before you go on to the next steps. So this is fairly rudimentary, right? So you can add a lot of details in here about what this actual wing plan form is going to look like. You know, adding things such as twist, changing the number of panels that you have. Don't worry about editing any of that, but if you want to come back later and, for example, increase your resolution of the vortex lattice panels that you have, you can change that as well. So these are kind of the computational elements that will be running for that three-dimensional vortex lattice case. But this will be good enough to kind of get us started, and then we can come back and adapt this and change this as needed. Now note, in this case, we've run this with the same foil. You can change your airfoils. So for example, if we wanted to run on, say, this middle section with a NACA 0012, you can do that, and that gives you this aerodynamic twist by having a different airfoil section in here. So let's put that on the outboard section as well, so that way it makes that more obvious when we're looking at this, that we have a separate inboard airfoil and a separate outboard airfoil, and then they're just blended at that section between the sections 3 and 4 for this particular wing. Now the advantage here is that you can then model a full wing planform that has multiple airfoils across the span by inputting different airfoils, or you can actually include flap effects. So now that you add a different airfoil with a flap on it, you can actually have the for that particular airfoil section. So for this particular problem, what you're going to be doing is actually creating a flap on the NACA 652415 airfoil, running that for -5 degrees and 10 degrees, and then placing that at different section locations across the wing. So you'll need to create these airfoil sections with that correct geometry for the wing, indicated by the locations of the flaps and the ailerons respectively, with the flaps deflected at 10 degrees and then the ailerons deflected at either -5 or 10 degrees for the port and or starboard wings, and then come back in and then rerun that. So for this example, I'm just going to keep this with the same airfoil cross section across the entire wing planform, so we don't have to worry about it. And that's it. So that's all you have to do. Again, note that that was pretty straightforward going through this process. So now we have our wing, and then we can go through the analysis routine. So we're going to come back for this three-dimensional geometry then and define an analysis. Note again, we have some different type options that we can run through for this particular case. For now, just fix with type 1, which is a fixed speed. You can come back later and look at fixed lift cases. That's very useful in a real aircraft case where you're going to be keeping your weight the same, assuming that you want to maintain level and steady flight. You also want to maintain the same amount of lift. So as you're changing the angle of attack, you're also changing the velocity of your aircraft in order to maintain that lift equal to weight. You can also look at fixed angle of attack and then look at side slip cases where you're changing the beta. So we'll come back and look at these later in the semester. Right now, let's just do the type 1. So we're going to fix the speed and then vary the angle of attack. So I'm just going to select 100 feet per second here as a good place to start. So that will allow us to just see how this works. Now it is important, what I want you to do is use the horseshoe vortex, the vortex lattice method 1 with no slide slip, and turn off viscosity. So we're just going to run an inviscid analysis. There are some other options here that you can come back and change later, such as changing the plane inertia, changing reference dimensions. Again, these are going to be determined by the geometry that you input. So if you fix that earlier, you don't have to worry about that. Changing things such as aero data, putting in a ground effect, and also adding extra drag if you need to. So if you know that you have, for example, antennas, maybe landing gear on your aircraft wing that aren't going to be modeled correctly in the vortex lattice method, you can actually add them in here as part of your drag buildup. But for now, we just need to worry about changing values within these first two sections, and then we're good to go. Now, once you do this, you can set up a sequence again, analyze it, and that's it. And so notice very, very quickly, this is a very rapid solver, is you end up having your pressure coefficients and, although it's kind of hard to see here, your actual lift distribution profile across the wing. Let's go to a slightly higher angle of attack here, get a slightly larger value. So now you can see your pressure coefficients. These are your CP values across the wing, as well as your lift distribution. Now we had a fairly coarse grid for this particular wing, so it doesn't really show up in as much detail as we would like. So it would probably be preferable if we went back and added some more sections into each one of these wings, so that way we could increase the resolution for this particular analysis. Now note, you have a lot of options here that you can run through and look at in terms of the final results. You have your induced drag values. So this is your drag due to lift. So it's showing you how much drag that you're generating. You can also look at the moment that's being generated. We didn't do viscous drag, we kept that off. We have downwash on right now, so that's kind of hard to see, but it's right here in the back. Surface velocity, so I'll go through and calculate this for us, so we can actually look at our values of velocity along the panels at the surface. And then finally, if we want to, we can also plot streamlines. We'll calculate these and then show us what those streamlines look like coming off the wing. We can see our vortex roll up here. Now when you add the flaps and ailerons, you also see the vorticity coming off from that. Now once you've done this, then you can start to come in and play with a build-up on this. You can come back and look at your plane geometry. For example, you could add in that horizontal tail plane in the back. So you could throw this in here. This is actually going to be pretty close. So we're going to move this back a little bit farther. We could define the size of this. Let's make it a little bit bigger. This is not going to be the correct size for the Piper Cherokee because again we'd have to go back and look this up, but we're just going to throw something in that's going to give us something that's going to be a little more realistic for the actual size. And then once we get this, we can select an airfoil. Let's put the 0012 in for each one of these. There again, our panels. We can save and close that out. And then we will actually have a tail in the back. And notice again, this is a pretty large tail compared to our wing, so there's nowhere close to the actual size and location for what we'd have on the Piper Cherokee. Again, this is just used as an example, and then we could run through and do a full analysis of this. And so it not only gives us the pressure coefficient on our main wing, but also on our horizontal tail plane. We could throw in a vertical stabilizer in there then as well, and then also start to define a fuselage, but we'll come back and do that later. That's it. That's enough to get us started, so that way we can start to model the wing geometry on the Piper Cherokee. So start playing around with this. Again, this should be enough information to get you going and to let you solve this particular problem.